Weather radars have been successfully used for many decades to monitor severe weather and estimate precipitation accumulation. They are an extremely valuable tool for analyses of rainfall events and have many advantages, including their high spatial and temporal resolution. However, because they do not measure precipitation rate directly, they are prone to many types of errors. Proper radar calibration is essential for producing high-quality weather radar data. An improperly calibrated radar can lead to significant errors in reflectivity measurements and consequently precipitation rates. A difference of plus or minus 4 decibels translates into a doubling or halving of the rainfall rate. Anomalous propagation occurs when a shallow layer of cool, moist air near the ground causes downward bending of the microwave rays emitted by the radar and produces echoes from ground targets that would normally be below the radar beam. Unfortunately, the temperature and moisture gradients that cause anomalous propagation usually accompany precipitation. Clutter occurs from the radar beam reflecting off terrain or other objects such as buildings, trees, birds, or insects close to the radar and can lead to an overestimation of precipitation. Beam blockage occurs from terrain partially or completely obscuring the radar beam and is a major source of error in mountainous areas. While beam blockage can generally be easily corrected for, it still affects the radar scan strategy and can lead to blind spots near the ground. Attenuation is weakening of the radar beam as it moves away from the radar and can be caused by atmospheric gases, precipitation, and a wet radome. Attenuation by atmospheric gases is easily corrected for. Attenuation due to precipitation can lead to an underestimation of the rainfall rate. It is dependent on the precipitation intensity and the transmitted wavelength, as it affects shorter wavelengths more significantly, especially at long ranges. While the radome is important to protect the radar components, especially in intense precipitation, it causes attenuation when wet. This can be minimized by applying a hydrophobic coating such as wax, which makes the precipitation stay in drops rather than create a continuous film on the radome. Beam overshoot occurs due to the curvature of the Earth and standard refraction, causing the radar beam to become higher above the ground at longer distances. This leads to the radar beam overshooting the precipitation and underestimated precipitation rates, or even a lack of detection. Below beam effects occur due to the height of the beam creating blind spots near the ground, where the precipitation being sampled by the radar may not be representative of what's happening at the ground. Strong, low-level winds can move precipitation away from the location of the storm. Evaporation below the beam leads to an overestimation of precipitation, and growth by collision coalescence under the beam leads to an underestimation of precipitation. Non-uniform beam filling occurs when the beam is only partially filled with hydrometers. This leads to an underestimation in precipitation because the returned power is averaged over the entire sample volume of the beam, which results in a low calculated reflectivity. Errors in precipitation estimation occur when the radar interacts with hydrometeors that are not liquid. When the radar interacts with the melting layer, the melting hydrometeors have a much wider cross-section than typical raindrops and are coated with water. So in this layer, reflectivity values can be 5 to 10 decibels stronger than the rain below, leading to precipitation estimates up to 10 times larger than what's happening at the surface. The presence of hail can lead to anomalously high reflectivities and overestimated precipitation rates. Hail contamination presents a challenge because it can occur both in storms with high rainfall rates and storms with relatively low rainfall rates. Errors can also arise from the equation that relates reflectivity to rain rate. This equation is related to the size, shape, and number of hydrometeors present, also known as the drop size distribution, which can vary from storm to storm and even within the same storm. Use of an unrepresentative equation to relate reflectivity to rain rate can lead to significant errors in precipitation estimation. While many improvements have been made in processing radar data to help correct sources of error, some limitations still remain, even after decades of research on the topic. Despite their limitations, radar-only products for precipitation estimates will continue to be useful, mostly because of their ability to capture the high spatial and temporal variability of rainfall events.